That is, find out conditions under which this is actually the boundary. Of a complex manifold. That's called the embedding problem. And we also study the Yamabe problem, that is the first basic nonlinear equation you can study on this manifold. That is to find the extremal of so-called quotient. So it turns out the answer to both questions, at least our answer to both questions, depends on knowledge about these two operators, namely the CR component of Laplacian and then the Penny's operator. So for example, for the Yamabe problem, we find out under these assumptions you can solve for the optimal global quotient, and you get a number. It's called the Yamabe quotient, right? So y of theta, we know that this is a number which is always less than y of theta naught on the, say, standard canonical 3-sphere. And so in some sense, this number determines whether the manifold is the same as S3. It's a nice number, but this number is very hard to understand because you have to do a minimization problem. So it's highly transcendental. So in this last lecture, I want to talk about trying to find global CR invariants. Global CR invariants. Similar to numbers such as these, so that if you know something about these numbers, maybe you can tell what the manifold is. Okay, so that's the goal is sort of trying to understand the global equivalence problem that Xiaojun has been talking about, the local version. Okay. So when we did that, I introduced the following gadget, right? So thanks to Xiaojun's lecture, I can fill in a little bit on what he's saying there. Namely, this is in general now, so I'm looking at higher dimensional, general dimension CR structure, and then so there is of course, the analog of the Webster curvature. In fact, in higher dimensions, there's the Ricci tensor as well. Okay. So in higher dimensions now, you take the Webster's connection, and that gives rise to curvature tensor. That's associated to this particular choice of compact form. So I can write more or less the same way. R alpha beta bar gamma.
That exists whether or not it's a boundary of the.
Yeah, it's an abstract CR structure that always exists.
In the three-dimensional case, I think every C manifold admits a almost complex structure.
Yes. Yes.
Almost
complex structure.
No, contact. This.
Well, every three manifold
admits a theta and
admits a contact structure. That's no.
But
yeah.
That's not true in that higher dimension case.
That's not true in higher dimension case.
So,
yeah.
Is there any integrability restriction in the C manifold? In the C manifold case,
that's exactly the reason we introduced this Penny's operator, because in three dimensions.
Yeah. But
there are many.
Are there topological obstructions to getting the integrable?
The question is what is integrable? Right? There's no local formulation of integrability.
Yeah.
So you need a global condition. And that's what this condition is for. That allows.
So is there a topological obstruction
To?
for a three manifold to admit that it will never be a boundary of a complex manifold?
Well, that's exactly what we're saying, right? We know that if this is not satisfied, for example, the Rossi example tells you it's never the boundary.
Okay.
Yeah, but it's not. The obstruction is not topological. The obstruction is complex on the J. Because that's the same structure on S3. It's just slightly changing the J, then it's never the boundary. So it's not topological obstruction. Okay. Yeah. Okay. Well, thanks for these questions. So, and then maybe I should list this. So the main question, say, the main question depending on what you're interested in. But if you're interested in contact topology, then I take a three manifold. We ask how many distinct contact structures you can put on without talking about the J. Okay? So we talk about this up to contact equivalence. Right? This is a nice problem given the three manifold. How many different contact structures you can put on. This is the one remaining open question on three manifold topology. Yeah.
What is expected?
Huh?
What is expected?
What is expected? Well, that means I'm going to have some conjecture. Okay. Let me explain. The purpose of the lecture today is heading toward that direction. Okay. So, but what is known here is that there's a work of Eliasberg, and then I guess all the Sproler, homology, three-dimension, various construction of homology trying to answer this question. Okay? And we are coming from differential geometric point of view, so we want to look at curvature invariance, which help us understand this question. So this is really, for topologists, this is the main question. Okay? But for people working in, say, geometry, CR geometry instead of contact topology, then we want to know to find enough CR invariance to maybe at least roughly classify, right? Classify. Now, instead of just the contact topology, you classify this J into, say, several large classes. So there are really two basic questions we're trying to answer. Okay. All right. So now, in terms of the curvature invariance, so this morning, Xiaojun was writing this down. So you have this Chern tensor. And then you have the Skelton P alpha beta bar G gamma bar and then minus certain multiple. So let me write it out, okay? I prefer just to write it this way. Product G. So this is what we call the Chern-Moser control of Y curvature. The decomposition is just like the Riemannian case. Okay? That's the way Alice explained it earlier. Okay? So what is this P alpha beta? So P alpha beta is 1 over n plus 2 R alpha beta minus 1 over 2 times n plus 1, scalar curvature times T alpha beta. Okay? And
can you explain this constant a little bit?
oh,
Why it's 1 plus 2?
well, you
No.
dimension is different, everything different. Why do you expect everything to be the same?
Okay, so this dimension is a change, 2n plus 1.
Yeah.
That's the same as our constant.
What?
I'm sorry. It used to be like we have
This
1.
this n refers to this n. Yeah. Yeah.
That's fine.
Okay. So T is the trace. Okay? And this is really a multiple of the scalar curvature, just like in the conformal case, but the constant is slightly different. So now the important thing here is the following. If you now change the contact form, if you change contact form to say exponential 2w theta tilde, then of course this thing only changes by scaling, just like the biotensor.
The alpha beta or alpha beta bar?
Thank you. Okay. So this just changed by scaling. So the only part that really changes, changes drastically, that involves the derivative of this compact factor here, then that's incorporated in here. Okay. All right. So let me continue here. So just like in Riemannian geometry, there is also Bianchi identity here. Okay? So there's Bianchi identity. So Bianchi identity is very important for people doing conformal geometry, right? Remember, Bianchi identity more or less says something like, in spirit, that says, you decompose the curvature into two parts, right? The conformal invariant part, and then this, basically we call it the Ricci part. So Bianchi identity relates the derivative of the Ricci part to the derivative of the bio part. Okay? So this is an important relation. Relates derivative of Ricci, or what I call P, to derivative of the bio, or what I call S. Huh? Okay. So Bianchi identity. All right. So let me write it out. So I'm only interested in 3 dimensions, so I write out the special case in 3 dimensions. Okay. So Bianchi says, I take the divergence of the skeleton. It's the same as differentiating the trace, and then plus n minus 1 times derivative t times. So when n is equal to 1, this thing disappears. Huh? Okay? And 0 derivative of the scalar curvature is a very complicated thing. Essentially, plus it's conjugate. So when I do conjugate, I lower the indices, so you see everything this way. So what is T alpha? So T beta is equal to 1 over n plus 2. Gradient of this trace of what we call this skeleton, analog of skeleton, okay? Minus I, and then covariant differentiate the torsion.
Do you mean T alpha?
Yeah, T beta bar. Sorry, now the way I have it is lower. Okay. Okay. So I want to explain the close relationship of these expressions to the condition for Fourier harmonic function. So Fourier harmonic function satisfies the following condition. Okay, in dimension greater than 1, I mean n greater than 1, that means the real dimension is greater than 3. We have just Hessian minus 1 over n, and then I take basically the sub-Laplacian, and then u h alpha beta, g alpha beta. Okay? So this is the condition for u to be Fourier harmonic when n is greater than or equal to 2.
Gradient gamma and then
And then, when n is equal to 1, remember we have to go to a higher order equation. So that's what we call the P alpha. The last time, this P alpha is not, sorry, there are too many P's. Okay, this doesn't mean the scalar function P differentiating alpha. This is an operator, P alpha of u. Okay, this is gradient alpha, gradient beta, upper beta u minus plus I A alpha beta, gradient beta u.
that's the definition.
This is what I used to call P3.
What would you
Okay,
say?
but now P3 is a one form, so I have an index for that. Maybe I should say P3U alpha outside. Okay. Okay. So now we want to look at Einstein condition. Okay. When you're in higher dimensions, in Riemannian geometry, to simplify the curvature tensor, you want what's called the Ricci tensor to be multiple of the metric, and it's called Einstein condition. So we ask, what about, in CR geometry? So we have this notion of pseudo-Einstein. So this is the first formulated by Jack Lee. He was interested in constructing compact form whose Ricci tensor satisfies the pseudo-Einstein condition. Okay. So we can write it out. Okay, it's just like the Riemannian case. That is R alpha beta bar is the Ricci minus 1 over n scalar curvature times G alpha beta bar to be 0. Okay, that's the condition when n is greater than or equal to 2. But when n is equal to 1, this vacuous is always satisfied. So you need a more strict condition. Okay? And that turns out to be gradient of R scalar curvature minus I divergence of the torsion when n is equal to 1. Okay. This is called the pseudo-Einstein condition. Now, in Riemannian geometry, if the metric satisfies the Einstein equation, then you can show, using the Yankee identity, that then the scalar curvature is constant. But here, because the Bianchi identity here involves extra term, so it's no longer true. Okay? So even though you have a pseudo-Einstein metric and pseudo-Einstein compact form, R need not be constant. Okay. So there, once I see things this way, of course, it occurs to many people that then what about, instead of constructing a contact form with constant scalar curvature, what about constructing a contact form which is pseudo-Einstein? Okay. So, one, find pseudo-Einstein metrics, contact forms. It turns out this is actually an easy problem. I will explain. almost right away. But while we do this, let me just record. Then the Q curvature, fourth order Q curvature, remember it has to do with this P3 operator. So Q curvature is in fact minus 4 over 3 divergence of this T operator. Okay? So now all the players are there. Okay? So I think I should erase this. Maybe erase the top here. So, very early, in the 1970s, Charlie Fettleman studied pseudo-convex domains. Because he was trying to understand how to construct the invariants for pseudo-convex domains. So, he introduced the following equation. Suppose now M is the boundary of a domain in Cn plus 1. So the dimension now is 2n plus 1. Yeah? Okay? So suppose now this is a hypersurface, real hypersurface, which is strictly pseudo-convex. Okay. So you look at the following determinant. Okay. J of u is minus 1 to the power n. Determinant. So this domain is Cn plus 1, so I'm just using Cn coordinate differentiation. Okay. So I look at this matrix u sub beta bar, differentiating in dv c beta bar direction, and u alpha, and then you write down this matrix u alpha beta bar. So he has asked this question: can we solve this equation equal to 1? Okay, where u is going to be a defining function. So u is greater than 0 on omega, and u is equal to 0 on boundary of omega, and you want du doesn't vanish there. Okay. So he formulated this problem. He asked, can you solve it? Of course, other people, say people like Alabi, they were already looking at such an equation without knowing what Fettleman was doing. But then the important thing here is the following. So this is an important remark. For such u, d bar, I d bar, u is positive, so I can take log. Okay? So you can use that as a Taylor metric on omega. So this defines a complete Taylor-Einstein metric in the interior of omega. Okay? And of course, back in the 1970s, Chen and Yao.
So you want to assume U is a strongly plus harmonic, right?
Huh?
Plus is not U is strongly plus harmonic.
He said it, but he didn't write it.
Defining function, strictly pseudo-convex.
I know, but you want U to be strong still.
It will be a consequence.
Plus harmonic.
It will be a consequence of this equation. So Chen and Yao says this equation can be solved. However, before they solved this equation, Fettleman introduced an approximate solution. To this equation. Let's call it stop. And this approximate solution is actually used by Chen and Yao as a barrier for their solution of the PDE. Okay, so the approximate solution came before these guys. The iteration scheme is actually very simple. The iteration is very simple. It says you start with any psi defining function. Okay? You just compute J of psi. Okay? And then you set the first iteration U sub 1. So not derivative. The first iteration to be what is it? Psi over J of psi to the power of 1 over n plus 2. And then after that you iterate. Suppose you have found the S iteration and you want to look for, but suppose you have found the U sub S minus 1, then you set the following iteration to be this guy times the following simple expression 1 plus 1 minus J of U sub S minus 1, and then divided by n plus 1 minus S times S. This is for S between 2 to n plus 2. Okay. Notice in that range, this thing is not going to be 0. Okay. Okay, so what's going to happen? Then at S equal to n plus 1, then you see that J of US is actually equal to 1 plus big O vanishing order S to the, defining function. So defining function is U, so U to the n plus 1. Sorry, S plus 1. So if S is n plus 1, this is n plus 2. Okay. So this is
S plus 1 is upper or lower? Not the power.
there's no power, it's just the algebra multiply.
1 plus S plus 1 power. N plus 2.
Yeah.
But Paul, is that 1 over n plus 2 or n plus 1 instead in the point number 1? The JU, is that 1 over n plus 2? 1 divided by n plus 2 or 1
I think it's n plus 2.
But they are n plus 1 by n plus 1 matrix. So that's why I'm...
No, this is the power.
I understand, but your matrix is, everything comes out, right? We determine it 1 by 1 from the rows,
Yeah.
it will come out. So
Yeah.
there are n plus 1 rows.
Yeah.
So
No, so the matrix n plus 2 times n plus 2. Everything is
yeah,
n plus 1.
Okay, then it's okay. I was,
Okay.
I'm talking.
But anyway, it's a
factor.
it's a tremendously easy iteration scheme to find approximate solutions. Okay. So at that time, there's no notion of Q curvature, no notion of DC variance. And later on, people figured out. They say that now if you let U be such a solution, for at S equal to n plus 1, such an approximate solution.
So U is U at n plus 1.
Yeah, such an approximate solution, and you use that to define the compact form. Let's say that to be deconjugate of U. So this is what is the imaginary part of the bar. Huh? Okay. Okay. The one Children wrote out. Then lo and behold, Q of this compact form is identically equal to 0. Okay? But even better, before that, you see that this theta is actually pseudo Einstein. So many people who work on the subject did not know the work of Pfefferman. They keep trying to solve Q equal to 0 as a PDE.
But here, but the U is not smooth. They are looking for smooth convection.
U is smooth.
No, U is not smooth. It's
We're not talking about the exact solution, we're talking about
approximate solution.
the approximate smooth. You start out with a smooth function, you do this, how you see it's not smooth.
You
Well, I see.
stop at the finite stage.
Yeah.
Not a limit.
I think you're
But,
interested in the bound.
Yeah, our solution is not smooth. That's the exact solution. This is an approximate solution. It's always smooth.
Well, so this was computed by Sun Ying Li and Lu, yeah.
But they didn't know.
You sure that they used the solution from the Pfefferman method?
Yeah.
I think so. My impression is my brain is not working now. I think so. The problem is that it's not smooth solution.
If psi is a smooth function, you compute this, you tell me it's not smooth.
No, I think it's only Cn plus 1 up to a certain level.
If psi is C infinity function, where do I lose derivative? You're going to lose even the number of derivatives, it's not smooth.
The limiting is S10
Yeah. So I.
may not be for the
Yeah. So you.
Oh, you cannot go on. You are stopped at s equal to n plus 1. The next one you cannot do. Oh, sorry.
N plus 2, N plus 2. Yeah.
Yeah, sorry. Yeah. Sorry. Yeah. Okay? The process stops. That's because you cannot find the next
The
one.
Japanese conjecture is still open, but it seems like it's a solution.
No. Japanese conjecture is not open. It's open for something which is not a domain.
Okay.
If it's a domain, it's always okay.
You're right.
Okay. All right. So now let me make some remarks. Okay. So it turns out now the transformation rule. First, I point out, right? Start with any defining function, you get a pseudo Einstein. So there are lots of pseudo Einstein contact points. Okay. So now, here are the remarks.
Can you say a little bit why S equal to 1 plus 1 is such a metric?
Well, you just have to compute.
Okay.
Yeah, you just have to compute. You cannot explain it. You have to ask Charlie how he thought about this. If nobody knows how he thought about this. Anyway, here are the remarks. Okay, so if theta is pseudo Einstein, okay, and then you look at theta hat is exponential 2u theta, okay, then the new contact form is pseudo Einstein if and only if u is Fourier harmonic. You can see that now from the formulation because the Fourier harmonic function satisfy these equations. You plug them in, you see that still pseudo Einstein. And the other one is suppose q of theta is equal to 0. Okay, so something that's weaker than pseudo Einstein because q is the divergence of this tensor. This tensor vanishing means it's pseudo Einstein. Okay. Then theta hat is exponential 2u times theta has q equal to 0 if and only if u is in the kernel of this fourth order Chinese operator. Remember, the kernel of fourth order Chinese operator contains the Fourier harmonic function. Okay. So in other words, the set of pseudo Einstein compact forms are really in one-to-one correspondence with Fourier harmonic functions. And the set of compact forms with Q curvature equal to 0 is in one-to-one correspondence with the kernel of the fourth order Chinese operator. So this picture wasn't known to many people. Okay? But that's the background. So from this point of view, it's obvious that we should be working with pseudo-Einstein compact forms and try to pick a good one among these if you want to try to classify your CR structure. Okay. So now, what I want to do is say, okay, you want to deal with Fourier harmonic functions. And there's no more operators you can do, right? You can apply P4 to it, but it's always 0. Okay. So our game is to try to look for a new operator which controls the Fourier harmonic functions. Okay. And this is motivated by work of Tom Branson. Because this analysis first lecture, Tom Branson has this very interesting analytic continuation argument in dimension to construct a two-dimensional Laplace operator out of higher dimensional conformal Laplacian. People will say this is silly, two-dimensional, everyone knows it. Everybody knows everything. But on the other hand, this procedure gives you new information. Okay. So the background is the following. There's a paper of Goldberg and Graham that does the following. They study fourth order operator. So conformally covariant operators of order 4 on general 2n plus 1 dimensional CR network. Okay. Okay, so I read it out. Okay, it'll take some time. Okay. So this is called P4. P4 applied to a function f is first you start out with self-Laplace square applied to f, and then you take the read vector field, so covariant differentiate twice in the read direction. So 0 direction means differentiating in t. And then minus 4 times the imaginary part of this complicated expression, A alpha beta, now upper B applied to that. Okay. And then another equally complicated expression, now beta bar, and then P alpha B bar with 0 here. Now alpha. Okay. I'm going to explain what that 0 means in a minute, but let me continue writing. Minus 4 times n squared minus 1 over n, real part. Now, and P is the trace of this CR Skaldun tensor, and then I take covariant derivative theta plus n minus 1 over 2 q times f. Okay, the fourth order q curvature. That is, this operator always defines the fourth order q curvature. Okay, and the fourth order q curvature is something like this: sum 2 plus 1 squared n times n plus 2 sub-Laplace of p minus 4 over n times n plus 2, the imaginary part of upper alpha beta and then a lower alpha beta. Okay. And then more, minus 2 and minus 1 over n, a alpha beta. Remember, e alpha beta is the torsion squared, minus 2 n plus 1 over n, p0 alpha beta squared plus 2 n minus 1 n plus 1 q and squared, p squared. So this P0 is the traceless P. Okay. Okay. So this is conformally covariant operator. Okay. So the scheme of Branson is really the following. You pretend that these operators are defined in abstract manifolds of dimension fractional. And you take it in. Okay? So this is something that we decided to do, so this is joint work. Basically, everything today is joint work with Jeffrey Case. So we decided to say, so on a three-dimensional CR structure, first off, before we say P4 prime, so this is a new operator called P prime, also the P prime of F is going to be 2 over n minus 1 P4 F. Okay? So at least when n is greater than 1, we make use of this formula, n is greater than 1, everything makes sense. Okay? Now, when n is equal to 1, yeah, you're dividing by 0, right? So therefore, that forces you to look at functions which are killed by P4 when you let n tends to 4. In this expression, you can see, when n tends to 1. So in this expression, you can see when n tends to 1, it does converge to the fourth order Chinese operator. Okay? So this is equal to the limit 2 over n minus 1 P4F. Okay? For F, which is in the kernel of P, but we actually want it to be in the kernel of the third order operator. Okay? So when F is fully harmonic, this is 0. And we use L'Hopital to make this definition. Okay? A lot of people don't like this.
The kernel P4 contain all Flory
Harmonics.
harmonic function, but maybe larger.
Yeah.
So this definition of P4 prime is defined on this kernel.
It is, but it doesn't make it does not have good properties if you just use kernel of P4. Then you can use the operator. We're going to write down the exact formula. You can use that to define any function, but you will not have good covariance property. Okay. You see, the whole game here is we want to keep track of operators that are covariant. Okay. Okay. So, and then you notice that P4 prime applied to the constant function 1 is exactly the Penny's Q curve using this definition. Okay. But we want to compute what this limit is. Okay? We want to compute what this limit is. This long thing, we want to compute it. Okay? So here's the result of taking this limit. So when you take the limit, it's very laborious. So what happens is that we know that if theta is pseudo-Einstein, okay? Remember, we're allowed to do that because Beckman hands you a large number of pseudo-Einstein contact points. Okay? Then this operator is much better. P prime, P4 prime of F is just 4 times subalpha squared minus 8 times the imaginary part of this derivative A alpha minus 4 real part. Okay. This formula you can apply to any smooth function, right? So if you compare that with the original P4, it's something like sub plus square plus t squared, and then plus terms like this. Okay, we have thrown away the t squared. Okay, but once you have thrown away the t squared, this is a nice sub-elliptic operator. Okay, so you can now try to solve PDE. Okay, then we compute. This is also a long computation. So define Q4 prime is going to be the limit. Remember now P prime, P4 prime.
T squared is negative, so you said P4 is something in.
What?
T squared is negative, right?
P4 prime.
P4
We have thrown it out.
You throw it out?
Yeah. You see T squared here? I don't see T squared here.
Oh, okay.
No, you say P4 points.
P4 prime.
P4 prime.
Yeah. Okay, so 2n minus 1 P prime applied to 1. P prime involves differentiation, so it kills 1. So you're allowed to divide by n minus 1. Okay, good. So from the definition, really the same as taking limit was the 4 over n minus 1 squared. P4 applied to 1. So when you look at such a definition, most analysts will say, we don't want to study this. Okay? But on the other hand, let me convince you that it's actually a very interesting thing that goes on here. Okay. So let me explain why we look at such an operator. Okay? Remember, I started out today by saying we're trying to look for global CR invariants, right? Global CR invariance means that invariants that are, numbers that are independent of which contact form you choose. You can change contact form by a positive factor, this invariance will remain the same. So from the lectures of Alice this morning, in conformal geometry, we know that integration of Q is conformal invariant. Right? So what about integration of Q in the CR setting? Right? So this earlier work of Kengo Hirachi, he worked on looking for CR invariants. He observed the following. Suppose now M3 is the boundary of a strictly pseudo-convex boundary. Strictly pseudo-convex. Then, of course, there's a Sago projection. Okay? So, let's talk about L2 holomorphic functions with respect to theta versus theta. So these are L2 functions on the boundary. Okay? And you can talk about the projection to L2 L2 of theta with the theta intersect holomorphic ones. Because you have a L2 inner product, this L2 projection is well defined. Okay? So this work of Hirachi that says the following. Well, first of all, the work of Boutet. Boutet of Mondel and Schultzmann that this is given by a kernel function. Okay? So Sago projection is given by a kernel function. Right? First, you look at the point, say Z on the boundary, look at Z bar here. Then this is a projection to holomorphic function, though this function is holomorphic on the inside. So you can evaluate at Z on the inside. First, you do W on the boundary, you evaluate Z on the inside. Okay?
So, which part is on the boundary, what is inside?
Sago maps a function to a holomorphic function on a boundary.
Both the domain and range all are boundary functions.
Yeah, but a holomorphic function on the boundary extends to be holomorphic function on the inside. There's some basic facts, several complex variables, right? So now that means that I can define this guy from W is on the boundary, but Z on the inside is okay, right? And now you flip it. And then you eventually say, okay, now we can actually do it on the diagonal with Z on the inside. And then this thing has an asymptotic expansion. So constant over, say, if U is a defining function, it's actually just constant over U squared. And then the next term is the log term. As Xiaojun mentioned earlier, when he was talking about the Berkeley kernel, but Boutet and Monvel and Shostran, they proved that for the Segal kernel, there's a guy, something here. Let me just put it down. It's just a Q curvature. Log. Okay. And then, after the log term, there's a finite part and smooth part, but that's vanishing of order U.
So log U, the function in front of it is f. F restrict to the boundary is Q, but the f also have power series expansion.
Well, I'm not saying anything about that. Huh? I'm just saying.
I'm asking, is there U square log U term, for example? Is there U square log U term, or U log U term?
No, there's no such term.
No such term.
Yes. But anyway, so asymptotically, near the boundary, when U is very small, Segal kernel has this expression. This is Boutet Monvel for some function, G. And then it's the work of Hirashi that identifies it with the Q curve. Okay? So in particular, if you apply it to Fefferman's contact form, then you know the leading term here is actually not there. And you know it's zero. Okay? You don't have to be spherical. Okay? So that's very nice. But the disappointment is that, well, Q is a nice invariant, but on the other hand, integration of Q, theta with E theta, because of the transformation rule, this is a CR invariant, but unfortunately it's always zero. Okay.
So this follows from definition of Q, or it follows from the Segal.
From the work of Hirashi. It's not easy. Okay.
Because of the relation to Segal kernel and C sub, or not?
Oh yeah, you have to use it. Yeah.
So you don't have like one was so C is what? So C is smooth function, right? Yeah, C is smooth
Well, here I'm just talking about asymptotics.
Yeah.
So this is just a function on the boundary.
A function.
Yeah. But you can rewrite this in some other form. Like function times 1 over, and then this actually comes.
But you said that for some choice of U, you can make Q equal to 0. Is that what you said?
Yeah. Right.
I thought so Q is invariant though.
Q at the boundary.
At the boundary.
I mean, you can write this as Q at ZZ, right? But Q on the inside makes no sense, right? Q only makes sense on the boundary.
Sure.
So in Shostran's formulation, this is f of ZZ bar times log, right? If you're interested at the boundary, then he says when Z is at the boundary, this is equal to Q. When Z is on the boundary. And Fefferman's work tells you Q is, if you use this contact form, Q is 0. So at least the leading term here is now 0. Okay? All right. So it's a tremendous disappointment to Hirashi that this is always 0. But later on, Boutet, because this is always equal to 0. It need not even be a boundary of a domain. So this is always true for any almost complex structure.
So not necessarily better.
Yeah, so that's even worse disappointment, right? It's always 0. Okay. All right. So now, so what's the advantage of our Q prime? Well, it turns out the Q prime is actually very good. Okay. So I want to write out the transformation rule for Q prime. Okay. Oh, did I write down Q prime?
You write on 2 prime.
No.
2 prime is
Yeah, you
1 over minus 2 squared.
But I didn't give you the exact formula, right? So Q prime is equal to minus 2 sub Laplace of scalar curvature plus r squared minus 4 times A11. Okay? So this expression now looks very much like expression for force the Q curvature in conformal geometry that Alice talked about. Okay, you have a log square term. And typically people in CR geometry think about A11 as analog of Ricci. There's no Ricci, but you think about it as analog of Ricci. Okay. Oh, so before the transformation rule, just stay some together. So these are properties, okay? So P4 prime is actually self-adjoint. This is not so easy to see, and this is the work of Kengo Hirashi. Okay. About 2 years ago, we told him about such a thing. He got very excited.
When you say self-adjoint on the fluid harmonics.
On the program.
Yes. Because it's otherwise not defined.
Yeah. But on the other hand, now if you transform theta by, say, now, my co-author likes to write exponential sigma instead of exponential 2u. Okay. So when you make such a transformation, then you have exponential 2 sigma P4 prime hat for the new contact form applied to a function is the same as P4 prime applied to F. Unfortunately, this is different from the P operator in conformal geometry. There's an extra term, P4 times sigma. Okay? And then how Q prime curvature changes is recorded by the following nonlinear PDE. So this is Q4 prime hat is equal to Q4 prime plus P4 prime applied to this logarithm of conformal factor plus 1/2 P4 sigma squared. So these guys are not nice. Okay? But we have such transformation rule. Okay? But it follows now from this the last transformation rule, it follows that integrations of Q4 prime theta wedge d theta is now a CR invariant. That is, if you remember now, these expressions only define for pseudo-Einstein contact forms. So if you change from one pseudo-Einstein to another one, you use this transformation rule, you'll see that this integral is independent of the...
Where are those 2 other term drops?
Huh?
You integrate both sides, and
Yeah.
then where does the other
P4 is a pure divergence. So this one drops. P4 prime is a pure divergence, so it drops.
Why is P4 or is it why is P4 prime integration equal to 0?
It's a divergence.
P4 prime, both P4 prime.
Both P4 and P4 prime divergence. Okay. So we have a new CR invariant. And it's non-zero. You can check on the standard 3-sphere. This is actually 1. We have normalized things. So on the standard 3-sphere. So it's a non-trivial CR invariant. And it's not trivial.
So you're still talking about the boundary domain or talking about generally balanced CR manifold?
Actually, this is a non-trivial CR invariant for pseudo-Einstein compact forms. Because when you talk about pseudo-Einstein, you don't need to talk about the inside. It's given by a local equation. Okay. So now we have a theorem. But this invariant is really useful. So this is also joined with Jeffrey case. Okay, that says, now suppose N3 theta j is pseudo-Einstein. The Penny's operator, the P4 is non-negative, conformal approximation is positive. The usual assumptions. We have been assuming these conditions during all my 4 lectures. Okay. Then we know that the integration of Q4 prime over N3 theta which d theta is always less than or equal to the same thing on the standard 3-sphere. S3 canonical. Okay? And equality holds if and only if N3 theta j is biholomorphic to S3 theta canonical j.
This is like the first part of Kursky's where he said it's less than 8 pi squared.
Yeah.
First part.
Yeah. But it shows that now it's really important. Now you can tell the 3-sphere from other objects. Okay? Okay. So let me round out this last part by telling you about an important formula that tells you something about this Q4 prime unit. Okay? So there's an important relation to the Burns epsilon invariant. So this is dealing with a special situation. Suppose now M3 is the boundary of X4, and X4 has complete Taylor-Einstein matrix. Of negative Taylor-Einstein constant. Okay? So I really should write it this way. So theta is the contact form. I really should write it this way. So M3 theta j be itself is pseudo-Einstein. Okay. I guess you don't need it for Burns epsilon. You just for Burns epsilon you don't need extra assumptions. Then I remember, I don't remember the constant, maybe it's 2 pi squared. Euler number of X4 is equal to, so now on this interior, you have these term polynomials, C2 minus 1/3 C1 squared. And then on the boundary, you have this Burns epsilon.
Yeah, so you normalize. You have to subtract the C integral part, right?
Yep.
Otherwise, not integral.
Okay, so what happens here is that, So Burns and Epstein, they define this expression by transgression. Okay, look at this polynomial. It's a local invariant, so you can find the transgression. Chern-Simons transgression. Okay? But without assumptions, this expression is horrible. You don't know how to play with it. Okay? So now if theta is pseudo-Einstein, okay, then this expression here is the inside is actually Q prime. Theta with d theta. What is called Burns-Epstein integral. So this Burns-Epstein integral is determined up to the exact form. So you have the various choices. And what we say is that if you now assume pseudo-Einstein, we can find a very nice one, which is this Q prime curvature integral. Why is this nice one? Because this Q prime quantity, this equation is sub-integrated. You can use PDE, try to control it. Okay? Okay. So the obvious program is now, well, let me make one more remark. Okay? Make one more remark. So this is if theta is pseudo-Einstein. Okay? So the obvious remark is the following. This C2 minus 1/3 C1 squared is actually, for Taylor-Einstein metric, is actually a sum of squares of certain sectional curvatures. So it's always non-negative. So you're saying the order number is equal to this integral plus this invariant. So this thing here plays exactly the same role as the Weyl square for conformal geometry. Exactly the role of Weyl square in the conformal geometry. So now if you have such a CR structure here, the game is to try to deform the CR structure. So when you deform the CR structure, the inside complex structure also changes. So this number will change. So you try to minimize it, make this thing as small as possible. Therefore, this quantity is as big as possible. Okay? So what happens when this is actually 0? Well, it's well known. When this quantity is 0, omega is a ball. Okay? So C2 minus 1/3 C1 squared integral is equal to 0. This is positive integrand, so this is if only omega is bipolymorphic to the ball. Complex 2, so real 4 ball. Okay. So if you are trying to prove this, so the analog of the Thurston's problem, you take a three-dimensional, simply connected CR structure. You want to say it is the standard three-sphere, and you try to put on very good CR structure so that this becomes 0. Okay? So the obvious question. How to maximize integration of Q prime theta with d theta. On this N3, but then you want to do this for suitable J, right? You vary J. You can fix the contact form as long as pseudo-Einstein. Just fix it. Okay? Then you vary J. Fine. So our first result is really saying that if you can get this to be as big as that of the standard three-sphere, then you are the standard three-sphere. But what we do know about this question is that we actually know that critical points of this integral, theta works, d theta. When you vary J, satisfies the condition. Satisfies the condition that the Chern tensor this Q11 compound tensor. We call it compound tensor.
He's talking about three dimensions.
Okay. So vanished, i.e., spherical, low polar spherical. Okay. So if you start out with somebody which is simply connected, you are able to maximize this thing, then it's spherical. If it's simply connected spherical, it is the sphere. So this is the clear outline of a program to classify compact structures on S3. Okay? Of course, you can play the same game on compact structures on S3. Well, yeah. And I don't think the topologists even know how to classify compact structures on lens spaces. So here's a program that offers good possibilities, and we have some control on this maximum.
So when you change the form of the TA, you want it to be integral, right? I think otherwise the formula there is not usable. And also you want it's only bounce.
No. This guy you put on the standard compact form. You want to maximize it, so it's exactly equal to this guy. Integration of Q1, Q is 1, theta with d theta on S3 divided by order of n.
So I'm talking about
You just want to hit this number.
You said you're going to, so you fix the content form on M.
Yeah.
You're going to deform the content structure, right? And you have two conditions. One
Yeah.
is integral, one is embeddable. Probably that one, one is embeddable. The second, it only bounds manifold without singularity.
It doesn't matter, right? Because we have the theorem. If this is finite, if it's spherical, finite spherical, it is a quotient of sphere. You don't need to know what's inside. Okay? This is just motivation. We don't depend on it.
Oh.
Right? Yeah.
So this the proof of this theorem, you are using your solution of the Yamaha problem.
Well, yeah, of course. This thing here uses heavily our solution of the Yamaha problem.
And then sort of follow the idea that I was sketched
Yeah.
out.
You see, I can outline it, right? You solve the Yamaha problem, right?
That is clear.
The Q is, where is it?
You drop the A, beta, the tensor,
Yeah.
the torsion term.
Yeah,
Drop it.
sub plus R squared minus torsion.
Yeah, you can drop that.
Right? There's some multiple here. But if you integrate this goes away. Right? And the Yamaha problem says it's always less than that of the standard sphere. So if this is non-trivial, it's strictly smaller. I'm cheating a little bit. Because the Yamaha solution may not be pseudo-Einstein. But we know how to correct it. Yeah. But anyway, this is not an easy theorem. It depends on the solution of the Yamaha problem. Okay, I stop here.